Now let us understand little more about energy diagram. Okay, some planetary motion like that the motion that given by gravitation, attractive gravitational force. So F of r is attractive gravitational force is given by F of r is equal to minus g m1 m2 by r square. M1 and m2 are two masses. Then its potential is given by minus g m1 m2 by r, and the effective potential is U of r plus L square by 2 mu r square, that is g minus g m1 m2 by r square plus L square by 2 mu r square. Now I am directly drawing the energy diagram. So in this energy diagram, so r is the x-axis, energy on the y-axis. So this one, this is U effective, this curve, this black curve is U effective, and this is the L square by 2 mu r square. Actually that is the centrifugal force. Okay, centrifugal force. That centrifugal force is very important. That binds the particle. Okay, and this is minus g m1 m2 by r square, the gravitational force. Okay, here I can consider three regions of total energy. The red one are the total energy regions. The first one is this one, E greater than 0, and this one E equal to 0, E less than 0, and one more important is E is equal to E minimum, that is at this point. Okay, let us understand what are the importance of these points. I am considering the case where L not equal to 0, this one, L not equal to 0. If L equal to 0, there is no centrifugal force, the repulsive centrifugal. So this is a potential. So I can call the repulsive centrifugal potential. U of r is a potential. So dimensionally this also should be potential. I call it is repulsive centrifugal potential. Okay. So I am considering L not equal to 0. L have some value. So first case, E greater than 0 in this region. Okay. Let us understand what happened. Here R is up to this level. You can calculate the kinetic energy. As you know, kinetic energy should always be positive. So it can reach here and it will go back. But you know, up to at this point, that means for the lower values of R, it is bounded. But at higher values of R, it is not bounded. Okay, that means for large values it is unbounded, and for lower values it is bounded for a certain minimum value. This one we call it as the turning point. Okay, if barrier is overcome at this point, the particle will kept apart by the centrifugal barrier. Okay, that is the first case. Actually this is this kind of orbit is called a hyperbolic orbit. We will learn more about this thing in a later session. Okay, anyway, E greater than 0, the R is unbounded for large values. Okay, and this gives a hyperbolic orbit. Now E equal to 0, our this axis E equal to 0, what happened? E equal to 0 is almost similar to our E greater than 0 case, the first case. Okay, for large values it is unbounded, and smaller values there is a particular turning point. Okay, so but one thing is the boundary between the bounded and unbounded states are very small. Okay, in this case, and this kind will give you a parabolic orbit. Okay, this is a E equal to 0 is a parabolic orbit. Now the third case is E less than 0. In the E less than 0 case, both at large values of R and small values of R, it is bounded. Okay, for both small and large it is bounded. Therefore the two particles will form a bounded system. Okay, that's very important. And these kinds of system will give you, at this state the system will give you a elliptical orbit. Okay, so hyperbolic, parabolic and elliptical orbit. One more left is E is equal to E minimum, that means at least lower value. So at this point R have only one value, there is no more values. Okay, so R is restricted for a single value. So that means the particle will possess a constant distance from one another. Each particle will separated with a constant distance. Okay, that's very important. This kind of system will give you a circular orbit, right? Therefore hyperbolic, parabolic, elliptical and circular orbits, very important. So these are the energy diagram, and these are different orbits that will learn more about these things while we deal with planetary motion. And one more point is, what happen if L is equal to 0? When L is equal to 0, the particle move along a straight line and they will make a collision. Okay, and since L is equal to 0, there is no centrifugal barrier to hold the particle apart. Okay, they will come close each other and they will make a collision.